Successive iteration of dominated strategies is one method we can use to solve games. Um, the basic principle behind this solution method is to find moves available to either player that are strictly worse off, that make the player strictly worse off than some other move by choosing them. Conditional on what choices are available for the other player. So if we were to add, for example, a move Spock to rock, paper, scissors, where you would make the live long and prosper sign, and Spock is such that if you show Spock, you'll tie with paper and scissors, but you'll lose to rock. So you can either tie, or lose. Naturally, we would say we could infer that this is not going to be a good move to play, but we have to be careful in how we want to specifically show that Spock is a dominated strategy. So, for example, if I play rock, Spock might be preferable to rock because the opponent might play paper, and paper doesn't beat Spock, and paper does beat rock. So we would not say that rock dominates Spock, and so we can't eliminate it that way. What we can do, though, is compare it to scissors. So scissors beats paper, so in that sense it's better than Spock because Spock does not beat paper. And both scissors and Spock lose to rock. So in any situation where you would play Spock, you would strictly prefer to play scissors instead. So based on that, using successive iteration of dominated strategies, we would remove Spock from the choice set of the role player, and then by the same argument from the column player. So our 4x4 game became a 3x3 game because we've eliminated this move, Spock, as being valuable. So here's an example of a game. I've introduced the 2-number notation. So if I'm the role player and I choose A, and the column player chooses 1, then the result of the game will be that I score 2 points, and the column player scores -2 points. If I choose C and the column player chooses 2, I score 0, and they score -1. And we want to solve this game using successive iteration of dominated strategies. So we can eliminate row 3 because row 1 is strictly better for the role player. So this should be, so row C versus row A. Row C, 2 is better than 1. 1 is better than 0. And -1 and -1 tie. So anytime I would play C, I have a strict preference for playing A instead. So effectively, we can eliminate C from the choice set for the role player. Oops. So that would be an example of eliminating a strategy. So if I eliminate C, now I'm choosing between A and B. Now, given that, if I look at the column player has -2, 0, -1, 0, and 1, 0. So 1, 0 is strictly better than both of these. So we would eliminate 1 and 2 from the column player set. 3 is better than 1 and 2 for the column player. So that means we know for certainty that the column player will play 3, and therefore given the role player's choice between A and B, the role player will choose B. They have a choice between -1 and 0. So the role player will choose B. So we've actually solved this game. Role player plays B, column player plays 3, and we did it using successive iteration of dominated strategies. So here's a game. So I will be the role player, and you, the listener, will be the column. I will score either -1, 0, -10, or -4, and here's your score, and you'll pick. So I'll take about 6 seconds and choose your move, 1 or 2. I will choose mine, and we'll see the result. Okay, you've made your choice. I selected move B. So if you chose move 1, I'm sorry, you score -10 and I score 0, my best possible outcome in this game. If you chose 2, then we both score -4. So notice that this spot here is strictly better than this one for both of us. So you would say, why can't we agree to both just go here instead of going here? And that would be a nice thought. The problem is that if you agree to do 1 and I agree to move A, there's nothing stopping me from picking B in secret and then revealing and getting 1 extra point and costing you 9. And if I'm strictly selfish, then there's no cost to me for behaving this way. Using iteration of dominated strategies, we know that, well, we can eliminate A because 0 is better than -1 and -4 is better than -10. So in both situations, we would like to choose B. Similarly, 0 is better than -1 and -4 is better than -10, so we can eliminate 1. So the solution to this game is B2. This game is called the Prisoner's Dilemma. So many of these games have colorful names, and the idea, the setup for this game is usually described as, you have two people that get picked up for petty theft, which would have a prison term of 1 year, but they're given the opportunity to turn state's evidence. So they could turn state's evidence and go 0, and then the partner could as well. If they both decide to go evidence and rat out each other, they can end up plea bargaining and get a smaller charge, but everyone goes to prison. So the result is that when you've got 2 people who don't know each other's actions, they're in separate interrogation rooms, you don't know if your partner in crime will rat you out, and so you have no choice, at least looking at your own best interest, but to rat out your partner and hopefully get it, and for sure get a reduced sentence relative to what you would have got had you not chosen to rat out your partner.